Hello, this is Brian Washburn. I'd like to talk and give an introduction to angular momentum for a single particle and angular momentum for a system of particles. And I'd like to look under what conditions does the angular momentum of a single or a system of particles change. So let's just review the definition of angular momentum for a single particle. So what I have here is I have a mass and it has a momentum pointing in this direction. The way I'm going to define the angular momentum of a single particle, I'm going to use the symbol little l. Little l is going to be equal to the position vector r cross p. That's my definition. Okay. Again, what is r? R is a little vector, is a position vector that points from the origin to where the particle is at a given time t. That is r. Okay. And then p is the momentum direction, the momentum in that direction right there. Okay. Now notice I have this cross product, and so then if the vectors, for example, if this is the xy plane, the angular momentum is going to be always in a direction that's perpendicular to the xy plane given r and p. So the way I would calculate the direction of L is, using the right hand rule. I'd put my fingers in the direction of r, curl them in the direction of p. So if I do that, I'd put my fingers along this direction here, curl them in the direction of p, and then my thumb would point outward like this. So if I wanted to draw L as a vector, I would draw it out of the board like this. Okay. Now we can actually, we can prove this another way by making a simpler case by, saying r is equal to x hat, p is equal to y hat. And then, if we draw that, let's draw a very simple case where, say I have r is like this, and say p is like that, okay? And then I can say that, well, L is going to be equal to r. Well, r is going to be r x hat cross p y hat, okay? And that's going to give me the product of r times p times x hat cross y hat. Well, x hat cross y hat is z hat, and so that's r, p in the z hat direction. So that's pointing out of the page using a right-handed coordinate system. Okay. So what I'd like to do now is look under what condition is angular momentum conserved. So what I want to do is look at the rate of change of the angular momentum. So let's just get rid of these little notes right there. Okay. So let's first calculate the rate of change of the angular momentum and see, when is the angular momentum when it will change. So I'm going to calculate this dot. Okay, that's going to be equal to the rate of change of r cross p. Using the chain rule, I can say this is going to be r dot cross p dot, or p, sorry, plus r cross p dot. Okay, now if you look at this first term here, this term here is going to be 0, and the reason why it's going to be 0 is because, well, p is equal to mv, but that's equal to m r dot. Okay, so then the cross product of r cross p is going to be equal to m. Sorry, I'm going to take the r dot, m r dot cross r dot. Well, any two vectors that are in the same direction, or is the cross product, that's always equal to 0. So then I get out of this 0 plus r cross p dot, but p dot, that is f. Okay, so that is a torque. That's the definition of a torque. And so that's the main result for a single particle, is that angular momentum of a single particle will be changed if there's a net non-zero torque acting on it. Now, let me give one example before I go to a system of particles. One good example is that of uniform circular motion. The way to find uniform circular motion is I have a particle, and it experiences what's called a central force. A central force is a force that, or it pulls the particle towards the center or the origin in a specific case. And a good example might be, okay, I have a mass and end of a string, and the tension of the string pulls it towards the center. Okay, so the net force, so again, the central force is a uniform circular motion. What I have to have is a net force towards the center. As a result of the net force towards the center, the acceleration is towards the center because the direction of the acceleration is always in the same direction as the force. And then the speed, or really there's only a tangential component of the velocity. The speed is a constant. Now the acceleration changes because obviously the length of this vector doesn't change, but at some other time it points with the same length in opposite directions. So the velocity changes, but the speed does not. Okay, does that make sense? All right. Okay, so now what I want to do is I want to look at angular momentum for uniform circular motion. So if I want to describe, let's write down the velocity and in a cylindrical coordinate system. So what I can say is that, well, for the particle, phi is equal to r, the radius of the circle. That means that phi dot is equal to 0. That means that it doesn't change. It makes a circle. All right. And then remember, we can write in terms of, we can write v tan in terms of the angular speed. It's just going to be equal to r times phi dot, which is equal to a constant. Okay, that's going to equal to a constant. Now, let's write down velocity, okay, and the general expression for, because what we're going to do is we want to show for uniform circular motion that the angular momentum is conserved. That's what I want to do. But before I do that, I have to write down velocity. I'm going to write it in a cylindrical coordinate system, okay, rho dot, and then I'm going to get rho, we draw this in class, okay. Now, that's going to be equal to, well, the first term is 0 because rho dot is equal to 0. Rho is equal to r, okay, and then that's going to get here phi dot phi hat, but that is the tangential component, that is the tangential, or there's only a tangential component, but we're just going to call that tan phi dot, and that's what I'm showing. Again, the phi hat direction is in that direction there. Okay, so that's the direction of, and that's what I expect. Okay. Now, okay, and then the other thing I need to know, I want to calculate a position vector for the object. Okay, you'll see in a minute why I need to do that. A position vector is just going to be equal to r rho hat. All right, so now I have the speed, I have r. Now I can, what I'm going to do is I'm going to calculate the angular momentum of the particle. Okay, the angular momentum is just going to be equal to r cross p. Okay, well that's equal to r cross mv. So I know v, I know r. Let's just write it out explicitly. R, the position vector, and the momentum. I have this. Okay, that's the first term. I'm going to cross mass times. I'm going to write it in terms of r phi dot phi hat. Okay, that's that term there. Okay, now notice I'm going to get a term of rho hat cross phi hat. That's going to give me z hat. And then I have r times r. That's going to give me r squared. And so that's going to give me equal to m r squared phi as z hat direction. Again, I expect that to be up. Now that's an important result. That is the angular momentum associated with uniform circular motion. Okay, that is an important result. We're going to see that many times in the class. Now, what I want to show is that for uniform circular motion, the angular momentum of the particle is conserved. Okay, now let's show it mathematically and then talk about the actual reason why. Okay, so let me calculate now this dot. That dot is going to be equal to the rate of change of m r squared rho, so this is rho dot here, by the way, and then z hat. Now the only thing that's going to change is phi, and I'm going to get m r squared phi double dot z hat. Okay, now I can put together, let me write it this way, m r, and then I can write this as d dt of r phi. Okay, now so these are constants. Now what the heck is this thing here? Well, that's v tan. That's this guy there. That's a constant. So the rate of change of a constant is 0. Okay, so what I've shown is that the angular momentum for a particle that does uniform circular motion is equal to 0, the change in angular momentum. And you even say why? Well, the reason why is because there's no net torque acting on it. There's a force that acts on it. it's a central force, meaning it acts towards the center of the circle. However, that central force does not create a torque because the direction of the force, okay, if we were to draw the force, the central force points like this, okay? Well, so the central force points like this. That's the force acting on it. The position vector at that given time points like that. That's r. Well, they're anti-parallel, but the cross product between the two is 0. So the torque produced by this central force is equal to 0. That's a very important result. And the reason why is because central forces we see a lot of central forces. Gravity is an example. The universal law of gravity, that's a central force. Coulomb force, that's a central force. Okay. Actually, what I want you to do is think of a fundamental force or a force you've maybe encountered that is not a central force. Okay, think about that. Let's talk about that in class. All right. So let me talk a little bit about central forces because this is going to be very important. So let's consider two particles. I have m beta, m alpha. These are two arbitrary particles. And then I have a position vector r beta for the position vector for position of this particle. I have the r alpha, the position of that. And then I'm going to define a position vector between the two, r alpha beta. And this is a position vector that goes from beta to alpha. It points from beta to alpha. Okay. And this is a relative position vector, and I can just get that by subtracting these two vectors. Now, say that beta exhibits a force on alpha, and that force is given by F alpha beta. Again, our way the notation is this is the force on alpha due to beta. Okay, so that will be a force. It could be attractive or it could even be repulsive, but the important thing is it's actually parallel along. So if it's a force that's repulsive, it goes from here to here and pushes this guy away. The important thing is that the direction of that force, the force of beta on alpha, is going to be in the same direction. Okay, it's going to point like that. Well, that's a terrible line. Sorry about that, but I think you get my point. If I can draw a parallel line to here, well, it's going to be like that. So those are going to be parallel or anti-parallel, whatever you want to call it. Okay, that's really important. So that is a property of a central force. And a central force is, for example, a Coulomb force. Say the force is, say the two particles have mass and charge. Okay, say they have charge. Or actually, since we're talking about classical, let's talk about gravity. Say there's a gravitational attraction between the two. Okay, so the force of gravity, okay, is going to be equal to G, m alpha, m beta. Okay, and then it's going to be r alpha beta squared. That's going to be the force, and so that's going to be the force of beta or beta on alpha. Okay, so that's a good example of gravitational force. So gravitational force is central. The Coulomb force is central. I want you to come up with a force that's not central. Okay, all right. So central forces are really important. So now I want to look at the angular momentum for a system of particles. Okay, so what is a system of particles? It could be a bunch of particles in space, or it could be what's called a rigid body. A rigid body is an object where, again, it's a collection of particles, but the distance between two particles in that body doesn't change as a function of time. So it doesn't matter. And what we're going to do is look at the total angular momentum. So the total angular momentum. So if, say, I have a mth alpha particle here and I have an mth beta particle here, the total angular momentum of a system is going to be sum over all alpha of all the angular momentum of, sorry, that should be an alpha, obviously. So we sum over all those guys there. Okay, now, I'm not going to derive it here, but what we're going to show in class is that the angular momentum of a system of particles is going to only determine on the net external force. The rate of change of the angular momentum of a system is only determined on the net internal forces. Okay, and so we're going to show this for central forces, assuming we have a central force. Okay. Now, we'll do this in class, but notice that what's missing from this is internal torques. Okay. Okay, so again, maybe I said that wrong. So the rate of change of the angular momentum of a system only occurs if there's a net external torque. Okay. Now, what about those internal torques? Okay, there might be internal forces, but even though there might be internal forces, there may be no internal torques. But what about those internal torques? Somehow the internal torques don't contribute to a change of the system's angular momentum. And we're going to show that is due to central forces. So what's going to happen is all the internal torques for a central force is going to be equal to 0. Now you may ask yourself, so this is the main result is that, okay, the angular momentum of a system of particles will only change if there's a net external torque. Thus, if there is no net external torque acting on a system, if that's equal to 0, then L dot is equal to 0. That means L, the angular momentum of a system, is a constant, and that is conservation of angular momentum. Okay. So what we're going to show is that in class, and you'll read about this, we'll show why this is the case. Okay. And this is a very useful result. Okay, extremely useful result. All right. So why is this an important result? Well, let me give you an example. Say you want to consider the Earth rotating about the sun. So we have a two-body system, the sun and the Earth, and you ask yourself, okay, is the angular momentum of the system conserved? To answer that question, you have to say, is there any force creating a net external torque? Okay, well, no, for the most part. I mean, you could ignore other galaxies and other solar systems in practice. So you can say that, yeah, there's no external torque acting on the system of the Earth and the Sun. Thus, you can say that, hey, the angular momentum of the Earth-Sun system is conserved. And in fact, that leads to what's called Kepler's second law, which we're going to talk about in class. So this is a very important concept. Conservation principles are going to make solving problems much easier, okay, to do. Okay, so let's summarize. What we've done is we defined the concept of angular momentum for a single particle and a system of particles. The angular momentum of single particle changes only if there's a net torque acting, not even external, just a net torque. And so the angular momentum of a single particle is only going to be conserved. Angular momentum for a single particle is going to equal to a constant only if the net torque acting on it is equal to 0. Okay, that's for a single particle. For a collection of particles, we can say that, okay, the angular momentum of a collection of particles, only a net external torque is going to change the angular momentum of a collection of particles or system of particles. And we're going to have conservation of angular momentum if the net external torque is equal to 0. Going back to this concept of central forces are important. And for central forces, what happens is, whether I have a single particle or I have a couple particles, the angular momentum of the system of, for example, uniform circular motion, the force is central, and the angular momentum of that particle is going to be conserved because it's a central force, and that force doesn't create a torque on it. Okay, so that's it. We'll do more problems and talk about this in more detail in class. So take care. Bye-bye.